So this is another representation of the same thing to reinforce the same concept that your inputs and outputs are going to be vectors in neural networks, at least when we are looking at it now. Later on, we can think of them as higher dimension than just one, just a single dimensional array. We will look at tensors later on, but for now, let's assume all your inputs and outputs are vectors. And when we are transforming them within the layer, we will use matrices for weights. So a matrix times a vector will get another vector, and that will become the output of that layer. So if you don't have any model fx is equal to x, if you have a linear model or a generalized linear model, then your fx is equal to sigma, some function, nonlinear function sigma of w1 times x. Again, I'm not using the bias, assuming bias is one of the extra dimensions of input that is added at each layer, that is appended or concatenated at each layer. Now, if we add one hidden layer, then this will be the first layer of the neural network that will transform the inputs using a linear multiplication and a nonlinear function on top of that. Then we will multiply another weight and another nonlinear function, and that will basically give us the second layer of the neural network. So that's adding one layer. If we add multiple layers, then this is your first layer, this is your second layer, etc. This is L minus 1th layer, and this is your Lth layer. And that is just a more complicated function. That's pretty much it. And we can also think of loss as another layer, where all how you can see the layers is that there's a function inside a function. So we can take this entire function and put it inside the loss function, and that makes the loss also as another layer. So when we train, what training means is that we want to find the derivative of loss with respect to any particular weight, let's say weight j, right, j, k. So because it's a matrix, so we will take the jth matrix, kth, or let's say the small l, lth matrix for lth layer, and then the matrix will have two components that will be, let's say, I and j. Okay, so we will represent all the weights using three indices, one for the layer and the other for the position in the matrix, the row position and the column position in the matrix. So now we want to be able to find the derivative of the loss with respect to any particular weight, and the way it will be done is using chain rule of derivatives, and a particular way of storing intermediate outputs of your chain rule is basically what backpropagation algorithm is, that we will look at little later in this lecture. So where did this idea of neural networks come from? So it basically had inspiration in the structure of biological neurons, right? So in biological neuron, you have a nucleus, cell nucleus, and there is a cell body around it, right? And then there is a very large fiber that goes from that body, and that is called the axon, right? So basically these fibers are what makes our nerves, and at the end of the axon, what we have are these connections which are connected to other neurons, right? And similarly, this particular axon takes inputs from other neurons that might be around it. So what you can see is that these structures are called dendrites. What we can see is that each cell by itself is simple. Okay, it has a simple structure and it is repeated. The same simple structure is repeated, but it can do complex tasks when several billions of these cells are put together in a certain structure. It can do all the tasks, for example, the sensing that we do using our eyes, the sensing that we do using our nose, using our ears, and then the thinking process that goes on inside our brain, the sensing from our touch, and then the motor control of controlling our muscles in response to these stimuli, planning for the motion, planning for the control, walking upright, which is a very difficult problem. If you take just a stick figure and make it into a human form with different joints that can move, it's very difficult to keep it stable upright. But we do it right from around 1 year old all the way up to a few years before we die. We can control our motion for standing up and walking and running and playing basketball and whatnot. So all that is controlled by a network of neurons, which are by themselves very simple cells, but when they are connected together, the information, the knowledge resides in the connection. Knowledge resides in two things. One is structure of connections, and the strength of connections. Okay, so that is basically the power of Mother Nature, that over several million years of evolution, it repurposed several simple cells, connected them, and made us into a conscious being that is able to dominate on its environment. They're able to control other species to the extent that we are eliminating several species to our own detriment, and it can perform several tasks. It can think about spirituality, it can think about science, it can think about various other things and so forth. So several years ago, in the 50s and 60s, scientists such as McCullough and Pitts, they started thinking about how can we model these biological neurons using simple mathematical functions, and that gave rise to the artificial neurons that were inspired by real neurons. So basically, the neural networks are networks of these artificial neurons, and they're somewhat like the human brain or the mammalian brain. And the simple structure that can be thought of is the following. So let's say you have a particular input dimension x1, you have another input dimension x2 and x3. We multiply them with their individual weights w1, w2 and w3. So whenever you see an arrow and something on top of that, so basically this input is being multiplied, and the output is basically k times x. So that's the convention when you show these signal diagrams. And with that convention, basically w1 and x1 is getting multiplied, w2 and x2 is getting multiplied, w3 and x3 is getting multiplied, and the bias is multiplied with 1. So basically what we get here is wi times xi plus b, right? And then so that is the output that we get here, and that is sent into a nonlinear function. So let's call it z. So what we get out here is sigma of z. Okay, so that's the simple structure of a neuron, of an artificial neuron, and it is quite similar to what a biological neuron does. Let me not say that it's quite similar, but it's a simplification of what a biological neuron does. So in a biological neuron, you have the cell nucleus, and then you have the cell body, and then you have the axon, and these are the connections. And these other neurons that you have in the vicinity, they give off some neurotransmitters as signals to them, and depending on the strength of the connection, so this particular connection may be for another neuron, and depending on the strength of the connection, whether it is positive or negative, we have inhibitory for negative, and positive are excitatory signals, and there are different strengths of excitation, different strengths of inhibition. So those signals, how frequently these cells fire, depending on the strength of the signal, there will be a potential which is basically a change in voltage, and that voltage gets communicated to the cell. If it exceeds a threshold, then this neuron will fire, and whatever is the downstream neuron, that neuron will get affected, that will get a signal from this neuron. So what this function does is basically it acts as a threshold to see whether this neuron should fire or not. And what we know from our previous mathematics is that if this is your input z, then sigma of z, one way to model this potential is to model it using a threshold function, and that threshold function is going to be a step function. Okay. So this step function basically decides whether the neuron is off or on. So that's a simple idea of a neural network. Later on, we will see that these steps are not very useful to us because we want to learn and we want to get some directional signal, and that directionality is just not there in the flat regions. So for that, we need some slopes for gradient descent, and that's why we don't use these step functions, just as what we don't use them in logistic regression. So in some sense, neural networks are a generalization over logistic regression that we will see later. So what is the role of this activation function? So this step function is called activation function, or whatever function that we put, whatever nonlinear function we put here is called activation function. Okay, so it could be a step function like this, it could be sigmoid like this, and so forth. The idea of these step functions is that if we have layers upon layers of these neurons and we did not have any nonlinearity, then basically we need not have many layers. We are just modeling linear functions of linear functions, and those are not they can be collapsed into a single linear function. To give you an example, so let's say you have a matrix W2 and it is being multiplied with matrix W1 times X, right? So basically, let's say we have another matrix which we call W3, which is basically the multiplication of the two matrix. Then this f of x is as good as f of x is equal to W3 times X. So this again is a linear function. So by having multiple layers, we did not gain anything new. In fact, we added ambiguity into by having two matrices multiply with each other. So because of that, we never have, even for regression, we never have just linear layers. Some of the layers last but one layer. So except for the last layer, every other layer has to have a nonlinearity, and that nonlinearity comes from this activation function, which is sigma. So only with this activation function do we have some interesting functions that we can model. In a perceptron, this is going to be a step function, right? Here in neural networks, or in logistic regression, we had the sigmoid function, and in neural networks, we will have more choices. So if you are doing classification with neural networks, the last layer is going to be sigmoid or softmax, which is a n-dimensional generalization of sigmoid. And for regression, we'll just have a linear layer, but the any layer below the last layer is not going to be linear. It will have, this function is not going to be an identity function, it's going to be some nonlinear function. So let's go back to logistic regression, see how it is being modeled by a single neuron. So let's say we have input dimensions x1, x2 and x3, and for fun let's also add a bias for 1, and we multiply all of these with weights w1, w2, w3 and b, and we add all of them up and we put that inside a sigmoid function. So when we add all this up, let's say we get z, which is a linear combination of all the x's and the bias, and then we basically compute 1 by 1 plus e to the power minus z, and that is the nonlinear function. The output that we get is the logistic regression over the input dimensions x1, x2 and x3, or the logistic function on top of that, and that's basically the model of a single neuron. So we already know what a single neuron looks like when we studied logistic regression. So how is this logistic regression trained? Whatever output that we get, right? So this is 1 by 1 plus e to the power minus z. We compare that against some target value t, and that comparison is put in a loss function, and then we take the derivative of the loss function, and that derivative is in some sense sent back, and then from there it is sent back to all the three weights. And based on that we adjust the weights slightly. So basically what we are saying is that W1 is going to take the value of whatever W1 was in the previous iteration. So let's call it t plus 1, or iteration, let's call it n plus 1th iteration, and it was whatever it was in the nth iteration plus some learning rate eta, minus some learning rate eta times the gradient of the loss with respect to W1, right? So that is the update equation for the first weight, and similarly we have an update equation for the other three weights as well as the bias. So this is how it was being trained by logistic regression. And what is L? L is the cross entropy loss that we have already looked at. Now we can actually have multiple outputs, right? So we can have, for example, multi-class output. So let's say you are given a picture of an animal, and these are some characteristics that are extracted from that picture, and we want to classify it into two different types of categories, which is flies and cannot fly, right? Flies versus cannot fly. So that is one binary classification. The other is mammal or bird, right? So you have ostriches that are birds that cannot fly. Ostriches and emus are birds that cannot fly. And then you have bats and flying foxes, which are also another kind of bats, which are mammals that can fly. So let's say we have all four combinations of fly and cannot fly, mammal and bird. And what we can see is that there could be features that are important to both problems. So for example, has fur, doesn't have fur is important to both problems. Has feather, doesn't have feather is important to both problems. And then has wings, doesn't have wings is important to both problems. So these could be your inputs that are extracted using either like some tabulation or something along those lines. And based on that, we want to reuse those inputs for two different problems. Now we will have two different weights. So now you can see that the weight is no longer a weight vector but a weight matrix, right? So we have one vector here and we have one vector here. So the weight is going to be a matrix now. Okay, and similarly our loss is going to be a loss over the first classification plus a loss over the second classification, and they could be different weights for the two classifications. You can have a loss for the first classification plus lambda times loss for the second classification plus lambda 2 times L2 norm of weights for regularization. So now we have 3 weights here and 3 weights here. So we will get a matrix that will be, so if your X is of dimension 3 cross 1, we are going to have a weight matrix that is of dimension 2 cross 3, so that the output that we get, the Z output that we will get will be of dimension 2 cross 1. Okay, and then we will take the sigmoid over that, and that will give us the Y, which is also going to be of dimension 2 cross 1. Okay, so now you can see that your weight becomes a matrix. So if you have m dimension here, n dimension here, then you get m cross n, or rather n cross m here, right? So that's how we are transforming from m dimensions to n dimensions by using an n cross m dimensional matrix. But this can be done, is what I wanted to show. Previously we did not talk about multiple classifications, but that's how we will generalize from logistic regression onward to multiple classifications.